Good afternoon. My name is Jennifer Drake. I'm an associate professor in the Department of Civil and Mineral Engineering. This afternoon, I'm going to be talking about some of the recent research that we've been doing in my group in relation to permeable interlocking concrete pavement. I apologize for not being able to be there and present, and I hope to be joining you during the Q&A later at the end of this presentation. So my research group at U of T specializes in low impact development, and permeable pavement as one technology has been an area of study for several years. Today, I'm going to be summarizing some of the key research projects that we've had in the last 5 years. And I'll talk about 3 different areas. Maintenance, so we've conducted side-by-side equipment testing for the hydraulic restoration of clogged PICP. Winter operations, looking at winter surface friction and best practices for de-icers, as well as observing chloride concentrations in effluent from operational permeable parking lots. And then lastly, some really new research we're just wrapping up now, looking at the use of extended detention and generating evidence to support adaptive or smart drainage controls for permeable pavements. So to begin with, let's talk about maintenance. Permeable pavements are passive filters. They're designed to collect all of that sediment and manage it on site instead of moving it along with the stormwater downstream. And so over time, they become clogged. The material will accumulate. That's what we intend it to do. And as that material accumulates in the joints, it leads to a reduction in surface infiltration capacity. And so over several seasons, particularly if there's no attention or no operations, some kind of maintenance or restoration will be required. So in this research project, what we did is we constructed with ICPI a test pad of permeable interlocking concrete pavers and artificially clogged them. And then under this scenario, we were able to test in a side-by-side, reproducible manner several different maintenance technologies that may be available to property owners or municipalities. So you can see here in the picture, this is just a picture of our experimental site, and you can actually see the pavement as it's been clogged. So to clog this pavement, we built our own sediment from waste from local yards, municipal yards, and we graded these materials so that they matched the same size distribution that you find when you go to an operational parking lot. So we applied then this in an accelerated form directly to the joints. Measuring the same or the exact amount of mass that we wanted to apply and applying it directly onto the joints. This is kind of new because permeable pavement, so water most of the time is rained directly, so you're not actually getting run-on of stormwater. And so we wanted to have this dry material applied and then wetted afterwards. So you can see a picture here of one of the graduate students applying our clogging material. And then we applied a small amount of water following to keep things in place and also to prevent any wind erosion. So this methodology has now been published. So our intent is that perhaps other researchers who want to evaluate new technologies, that there's things that are impossible for us to be more comparable. And so any papers that you're interested in too, please follow up with me afterwards. I'm happy to share them. So once we clogged the surface, then we used ASTM C1781 to assess or quantify the surface infiltration. So it's a single infiltration test. We pour a known quantity of water into a ring and measure how long it takes to drain. Guidelines generally recommend that a PI requires maintenance when the results from this test fall below 250 milliliters per hour. And what we can see in the graph in the bottom corner here is that, following this clogging process, infiltration rates on each individual pavement cell were comparable. So So it was reproducible, and that we knew with confidence that we had clogged the pavement uniformly. So they were all starting with the same baseline clogged condition, so that it would be a fair comparison when we evaluated the different maintenance technologies. So we tested 5 maintenance technologies, and these were selected consulting with industry to pick technologies that not only were likely to be effective, but also technologies that are generally available to property owners. So the first technology that we tested was supplied by the City of Toronto, and it was a regenerative air sweeper. The City of Toronto and many municipalities, this is their common fleet now. Cities have switched to regen air sweepers because they produce less dust and is important for urban air quality downtown. Then we also tested a specialized equipment called the PaveVac, and this is a two-phased system where first the pavement surface is treated with pressurized air. That's the circular head that you can see in the one photo, and then following, the disjointed or dislodged material is then vacuumed with a high-strength vacuum. So this is a product that is currently available in the US. I know that they have intentions for coming up here as well, and this was their first Canadian demonstration of this technology. Potentially fit into some of these smaller locations or odd corners that you might have on a pavement surface. Another common maintenance approach that particularly for small installations, say like an individual driveway, residential driveway, or a walkway, is pressure washing followed by manual vacuuming with a shop vac. So that was, again, a third treatment or technology that we tested. And then we tested a true vacuum. This is an Elgin Whirlwind, so this is a vacuum street sweeper. The last street sweeper that we evaluated was a waterless mechanical sweeper. This is the Elgin Eagle. So this is fully mechanical, doesn't involve water whatsoever, and was a newer street sweeping technology that was available. So here we have a little video again. joint. So here are some of our results, and these will be in a upcoming manuscript submission. We're still sort of finalizing it, but it's also available in a report to ICPI that was finished last spring. So what we found, first of all of the technologies provided restoration of surface infiltration. So that's very good news. There are lots of options for maintaining your permeable pavement. The most successful technology was, not necessarily surprisingly, the high pressured air and vacuum specialized equipment that's been designed, specifically for PICP. It was the only product that was able to consistently restore the surface infiltration to pre-clogging, like as built, brand new levels. And in fact, it was a little bit higher because when we were reapplying the jointing material, we didn't have anything to compact it back in. We were just putting it in manually with a push broom. So in fact, we found the results were higher than post-construction. The vacuum street sweeper also provided restoration in some places up to post-construction levels. However, it had a much greater spatial variability. And you can see in the colored picture on the far side, cell 4 is the vacuum street sweeper. And you can very clearly see the path where the vacuum head was located. One of the limitations, of course, with our test setup is we couldn't exactly shift the vehicles as tightly as we would want. But you can see here for actually implementing this, you would want to make sure that you were doing very tight and narrow strips, or perhaps even going in a hatch pattern and do more than one pass to get the best results. We saw that the waterless mechanical street sweeper actually provided very good performance. Again, you can see spatial heterogeneity, again, reflecting that there's going to be an area that has the maximum impact in the center of the vehicle. And so you may want to do multiple passes or hatched pattern passes. But this was really exciting because, there have been older street sweeping, mechanical street sweepers tested with very poor results, and these were quite well. And in fact, the waterless mechanical street sweeper was quite comparable to the regenerative air sweeper as well. Pressure washing was also effective, but of course this would not be feasible for a large installation. In general, we found that surface infiltration was correlated with the penetration, the joint penetration, or how much material was removed. And so this gives very simple visual indicators that staff can take on site when deciding whether or not they need to go over the surface with an additional pass, taking point measurements with a caliber. Will give you a very quick indication of whether or not you have removed the material uniformly and whether or not you want to go over it again. So the next project, and this project was actually running simultaneously in the winter months with our maintenance research, is looking at the use of winter de-icers and how to best optimize de-icing practices for PICP. So we are interested in winter performance for a number of reasons. The presence of snow and ice creates a number of hazards that we need to mitigate in the winter. First of all, we're concerned about our pedestrians slipping on a slippery or icy surface. And then we're also concerned about our vehicles skidding. So the action of slipping and the action of skidding are slightly different, but they are both affected by overall surface friction. And then also from an environmental perspective, we also care about road salt pollution. Sodium and chloride in excessive amounts can cause great amount of environmental problems, also even health hazards, and expedite degradation of infrastructure. So there's a lot of reasons why we should and would like to reduce the amount of salt that we use in the winter. I'll mention again that results from this work are available through a Transportation Research Record publication, and just be in touch if you want to get a copy. So over 2 winters, we set up a second test cell to evaluate different de-icing practices and how permeable pavement reacts to de-icing compared to conventional impermeable asphalt. So we evaluated friction with two sensors, and these are intended to simulate or replicate the action of a foot slipping. So as you can see in the video right now, this is our little foot that we adjust our angle until we find the slip condition. And unfortunately, I don't know if you'll see this video because I might be blocking it. Second one is to look at skidding. And so we had a slip alert, which is a little car, and we can assess how slippery a surface is based on how far that vehicle travels. So we had 4 test cells and then 1 asphalt control. The asphalt did have a slope and was drained to a mini catch basin because, of course, water's not going to infiltrate. It has to run off the surface. All 4 PICP cells were treated with road salt, applied at a recommended medium, 10 pounds per 1,000 square foot, and then low, 5 pounds per 1,000 square foot rate. And then we had 2 additional cells that were treated with the same road salt amounts, but the road salt was now pre-wetted with beet juice. So this is a green or eco product that some municipalities have been experimenting with or considered. The application or pre-wetting with beet juice changes the melting point, so it can allow the salt to be more effective at different temperatures, and in theory may allow you to achieve the same, de-icing effects with smaller quantities. Finally, the asphalt was treated with our regular medium road salt application as a point of comparison. So we instrumented this site with field cameras so that we could monitor for the presence of snow or ice remotely, as well as even get a sense of snow occurrences happening overnight. And then we had surface temperatures to look at temperature conditions on the pavement itself. So one of the interesting anecdotal events that we had is we actually had a flooding event on our asphalt control, which really talks, speaks volumes about the effects that permeable pavement can have in the winter. So what ended up happening here is we had a rain on snow slash like icy rain event on February 24th in 2019. And our catch basin, not being a fully sized catch basin and very shallow, ended up becoming quite filled with ice and couldn't drain properly. And so we had pooling water and overland runoff from our asphalt. So we had to go back in and we actually put a heat tracer through this to prevent that from happening again. But it shows, this is the challenge that we deal with in the winter. A lot of the urban flooding that we experience in the winter, it comes from things like our catch basins being clogged, our catch basin getting blocked with ice or blocked with leaf litter that wasn't removed before the snow hit, and then leading to poor drainage on the road and flooding. The permeable pavements, you'll notice in the little picture here, remained more or less free of water because the pathway, the infiltration pathway, is still active even in winter conditions. So we looked at a couple of scenarios. The first year, we focused primarily on shovel snow experiments, replicating as much as possible standard operations where you would have a snow event, crew would come in, they'd plow or they'd shovel, and then they'd throw down some salt afterwards. And we looked at then surface friction following. So as you can see, one of the things that is different between both the asphalt and the interlocking pavers is the surface texture. And we very quickly realized that there's a number of factors that influence the friction and the pavement's response to de-icing. The poured nature of the asphalt actually created a more heterogeneous surface that has inherently more bumps and rivets, whereas the precast nature of the pavers are inherently smoother. That being said, under dry conditions, they had comparable friction. So after we applied salting, we collected friction measurements immediately after, so normally 10 to 20 minutes, and then, or immediately, and then a second one 10 to 20 minutes afterwards, and then a third test 1 to 2 hours after. All of this would vary depending on the day. So as you can see here, red zone, it would be a very slippery surface. Yellow is going to be moderately surface, and clear is not slippery. And so when we would come and take the measurements before, just after shoveling, but before applying the salt, we would see that the permeable pavers tended to be slightly more slippery than the asphalt. And that is due to the just inherent, the pavers being a smooth surface versus the poured asphalt being much more rougher because it was a poured in place product, and poured in place by hand too, because it was so small. But very quickly, within 10 minutes sometimes of applying de-icers, you would see that the pavements had responded and were now trending to be not slippery. And in fact, we're responding faster than we were seeing the asphalt respond. And that this pattern then would continue as we moved a few hours away later. We saw very similar trends with the slip alert, or sorry, the Mark 3B, the one that's replicating someone tripping. Again, there being less friction before salting due to the differences in pavement, not permeable versus impermeable, and then comparable responses following icing or de-icing. We also noticed that the salt remained on the surface very differently. On the permeable pavement, we would regularly see complete granules, undissolved granules sitting on the surface. And what we realized would happen is because as soon as a small amount melts and infiltrates, the salt itself didn't get coated with water, and hence it could not dissolve. So it was left on the surface a lot longer. In contrast, what we would see on the asphalt is the entire thing would dissolve, and in fact, it would then leave a residue, almost like a brine residue across the entire surface. And I'm sure that picture looks very familiar to many of us. We've seen that in the winter. So in the second season, we moved on to looking at some ice cover events. And so we have a photo here. You can see in the top circle, our pavement now covered in ice, and then a little while later. Because we all know that sometimes we don't get in and shovel. We can have a freezing rain event overnight, or more often, people start driving on their vehicles in the parking lot or walking along a pathway, and that action melts a little bit of snow, which then refreezes later as something much denser and in many cases, in actual ice. And one of the things that this really causes is black ice. So what was really exciting about this work is that when we applied the here we go. My apologies. What was really exciting about this is where we could really see the opportunity to mitigate risks in the winter environment. So we had an ice cover experiment in our second winter, where, as I said, we covered the surface just manually by walking back and forth with a very thick layer of ice. And then we applied our de-icers. So as you can see, before we put the salting down here, everything was in the red zone, definitely definitely slippery. And then it took some time to, of course, respond to the de-icer for the salt to melt and dissolve, and then on the permeable pavement, infiltrate. Under these more extreme scenarios, we saw the benefit of the beet juice pre-treated salt. So you'll notice in the graph that you can see the higher application rates are more effective. Also particularly towards the end, the ones that had, we could do, beet juice and a higher application is going to be more effective. What was really interesting, however, was when we got to the end of the day and we reached sunset. So within, minutes, 10, 15 minutes of sunset occurring, you could see right away ponded water on the asphalt surface that hadn't been able to reach the outlet begin to freeze. And, over 20 minutes, we were able to see in that last group, you can see your black square dropping. The surface of the asphalt is becoming more slippery because that water has refrozen now as black ice. Whereas that hasn't happened on the permeable surfaces because the water's not on the surface anymore. It's infiltrated below. So this was, as a researcher, this was so exciting. No one's ever rigorously shown this. We all know that this is what people report from the field and from their pavements, but this was the first time we were able to show it with numbers, and I was so excited about this result. So we can see here, this is just with our other friction sensor, the same pattern. And then you can also see particularly just how much more effective the higher application rate and amended with beet juice. So that's the blue triangle. Not only is it the highest surface infiltration, but also the variability. So that's those bar lines was much, much smaller. You can also see in the photos below that the photo in the middle, which is the beet juice at the medium application rate, has the most bare pavement at the end of the day compared to the other plots. So this is all exciting. The location here that I was showing you, however, wasn't the best to actually look at chloride because it's not an operational parking lot. We were just putting down chloride or road salt when we were running our experiments. And so simultaneously, we have also been monitoring chloride concentrations from an operational parking lot in St. Catharines. So this permeable parking lot installation is with the City of St. Catharines at their Lake Street Service Center. It was built intended to facilitate research. So it has several different permeable pavement systems with separate monitoring chambers. And it was built as a zero exfiltration system, which is somewhat unusual, but also allows us, the direct opportunity to actually sample water that has infiltrated through the permeable pavement and the reservoir. So we instrumented each of these monitoring chambers with a weir box and a water level to measure flows, and a conductivity measure, which electric conductivity, which can serve as an indicator for chloride. Then throughout the winter, we went and we collected water samples, and then we would measure chloride and conductivity simultaneously so that we could create a relationship curve. And this allowed us to collect continuous chloride concentration data from an operational parking lot. This parking lot was salted by staff. Unfortunately, we were not able to get the quantity of material they put down, which is a disappointing aspect. But because these are zero exfiltration, we would anticipate that all of the road salt applied would make its way out. The only real question is how long is it going to take? Chloride is very non-reactive. It tends to be conservative. So most LIDs will not remove chloride, hence why we're so interested in reducing their use in the first place. So what we have here is our continuous data. So we were able to monitor a year and a half, and both during the winter and the salting season and the spring, summer, fall, and non-salting season. So what you can see on the top graph here is our chloride concentration data. So you can see we get big spikes in the salting season, particularly in 2017. You can see we had one event, our biggest event, where the concentrations were exceeding 20,000 micrograms per liter. So that's like halfway to seawater, incredibly salty. And then, there would be some salt levels in the non-salting season. Generally, though, these were low, although we did find instances where, if you look at towards the end, a little bit into the spring of 2017, where we were exceeding long-term chronic limits of 120 milligrams per liter. Below this is our just our precipitation data. So you can see, in the winter, your chloride concentrations often do coincide with rain events, but not necessarily. It has more to do as well with the temperature and whether you're having thaw or melting snow, as well as rainfall. And over here we have now a PICP. So first thing to draw your attention to is the scale of chloride concentrations, whereas on the asphalt, we had concentrations in excess of 20,000. In a PICP, we did not exceed 8,000. Now, this is still, orders of magnitude above environmental targets, but this is still a very, very significant reduction in magnitude. So you can see we get a large sort of amount. It is not necessarily coinciding with rainfall. Now, as we move into the permeable pavement, the graph at the bottom, you can see rainfall in blue and then discharge in green from the permeable pavement. And so, many times it may rain or snow and no water or discharge is generated. In fact, we still lose a fair bit of water just directly to evaporation in the non-salting season. But overall, we would still experience in non-salting years or seasons, exceeding chronic levels. But we did have great, attenuation effects during the salting season. We also used our flow data and concentration data to calculate event mean concentrations. And one of the things that we were curious is as researchers, including myself, have hypothesized that the salt we apply in the winter, we would see leaving the system in the summer. And from the data that we have here, this suggests that we aren't seeing that kind of detention that you notice, as soon as we start getting to April, there's a big drop in concentrations and then stabilizing down and then a little bit more of a drop towards the end of the fall. But really, it looks like, with the spring thaw, the majority of salt that we observe in the effluent is flushed from the system. The higher levels of salt that we do see, I suspect, are more related to the products themselves. The fact that all the aggregates are going to have some salts associated with them, cement, concrete, any of these construction materials, and that there is some weathering or even just fines, very small fines, construction dust, and so on. That is, a part of the water that we observe in the summer. So, last project that I'm so excited to talk to you about today is work we've been doing on extended detention. So this is a really interesting study, and this is a preliminary data. My graduate student is finishing this. I'm hoping we'll have publication on it later in 2021. We hear a lot of interest about smart infrastructure and adaptive management. And at this research facility, again, it was a series of interlocking concrete pavements that were built with the intention to facilitate research. And we had the ability here to control their underdrains and close or open them as desired. This was also a very low risk location to test things out because it's a walkway. So we don't have to worry about, maybe saturating soils for too long and causing structural issues. And so what we did over about 3 years is a series of either detention or extended detention operation. So we'd review, the incoming forecast. If it looked like it was going to be a good rain, we'd close the valves, force the water accumulate in the reservoir beneath the pavement and infiltrate into the soils which we, from our understanding, were highly clay and not necessarily super permeable. That turned out to not be the case, but regardless. And then, depending on when the next rain was forecasted, we would open the valves, allow for any remaining water to drain, and record the volume. So we'd do this, and then we would also, on other events, just allow water to drain freely with no detention and compare the volumes between these two. The other unique characteristics of this site is that we had 4 cells. 2 of them were more or less duplicates of one another, but the one cell here, which you can even see in this picture, was immediately adjacent to a building. So there actually was opportunity for it to receive additional water, rainfall that would hit the building surface and then drip down. And then the last cell, the cell closest to us, was actually had additional land that had old pavers that were impermeable, so impermeable pavements that were sloped towards it. So it had surfaces running on. And this is something that, we sometimes recommend. You can actually service, impermeable surfaces, have the water diverted or directed to permeable pavement and infiltrated there. So we were able to look at both, the condition where you just have your cell and you're only receiving the rainfall that hits it, and some of these other conditions that occur in some of our site design where maybe you do have a building or maybe you do have some additional walkways or parking lots that are impermeable that are draining to your permeable pavement. So I only have the one result slide on this because we're just sort of wrapping this up, but needless to say, the results are kind of very exciting. Our 2 middle cells, the PICP2 and PICP3, the ones that were just receiving rainwater, we didn't see any benefit to having extended detention. Something that we were surprised to discover was that this site was actually very well draining. There is sand like another meter down, and so there must be some fissures or some sort of heterogeneous thing there is some preferential flow paths that's allowing water to drain, because we had very good volume removals, much higher than we were expecting. So it wasn't that surprising that we didn't see any impact, by closing the valves or opening the valves, because water was free draining or infiltrating very, very fast, or faster than we expected to begin with. However, for our pavements that had additional water inputs, so PICP1, which is the one that was receiving the water from the adjacent building, and PICP4, which was receiving runoff from impermeable surfaces. If you just look at the box plots here, you can see, the white box, that's the one that has no detention, so you get much larger discharge volumes. And then the gray is when we force detention, and we can see we really removed some of these high events and been able to actually infiltrate a lot more water. So this is very exciting to show. No one has tried this yet, and so we're going to actually say that this is a useful approach. And what it means in terms of policy or management is that we're increasing the likelihood that we can manage a rain event. The number of times we're going to produce stormwater that needs to be delivered downstream, it's reduced. It's less frequent. And so there's big benefits in terms of mitigating the risk of flooding to the greater community. So super, super exciting, fresh off the presses, if you will. So what have we learned? I hope that this hasn't been too divergent, but I can never resist the opportunity to share, some of the new findings that were coming, because of course I love LID and then permeable pavement. But what are we seeing is really there's, permeable pavements are not the same as an impermeable, a conventional surface. They're stormwater infrastructure and transportation infrastructure simultaneously. They require their own operational practices, and can they achieve their purpose best when operated and maintained, treating them as a stormwater transportation hybrid system. What we've shown is that there are several types of technologies that can be used for surface infiltration, restoration, and that we have the first evidence now that we may be able to reduce our de-icing or road salting application rates without sacrificing pedestrian and vehicle safety. This is key. We have to show that safety is being maintained before we can recommend any changes or reduction in de-icing rates, and we've shown that. We've also shown that even with de-icing, we have the opportunity to have significant environmental benefits by shaving off these peaks that are very difficult for aquatic organisms to handle, where you suddenly switch to like super salty water. And we've also shown that I think the concern about this salty water being released at maybe another time of the year, which is undesirable, like in the summer when it's low flow and again, where organisms may be under stress. I don't think there's as good evidence as we initially thought that might be occurring. In fact, I think the majority of the salt is released by the spring and not in the later summer, hot, low flow months. And then lastly, we're now, demonstrating the real innovative opportunities that we have in terms of operations of these pavements. Things like extended detention, adaptive detention. The next logical step that we've done this very proof of concept research is to now codify and automate the operation of those valves and optimize them even so that we detain, long enough, but then are also ready to receive water when the next storm comes. So very, very exciting stuff, I think, all around. Just to sort of finalize here, there's always so many people I need to acknowledge and thank. This research was funded by NSERC, ICPI, Foundation for Education and Research, as well as some funding from the Ministry of Transportation and the Highway Innovation Infrastructure Program in years back. Site facilities were provided by Toronto Region Conservation Authority, City of St. Catharines, Canadian Masonry Design Center. The graduate students who actually conducted this work are Jody Scott, PhD student, Jeff Marvin, PEng, now working, Kirti Segal, PhD student, Tehimene Saravine, master's student, now working, Julia Zhao, also master's student, now working, materials provided by Lafarge, Brampton Brick, and others, street sweeping equipment, Joe Johnson, City of Toronto, Pave Tech, and then additional staff, summer students and other students from my research group that have really helped us out in a pinch. None of this could be possible without them. So that's the conclusion of my my presentation. Please, by all means, send me an email if there's some information you would like more on. You can also follow me on Twitter, and I really look forward to hopefully answering some questions live in this discussion that follows. Have a great afternoon, and thank you again for attending.